Okay, so welcome back. Logistical thing, any logistical stuff, finding things on the course website, for example, things that, all right. I will remind you that the first problem set is due a week from today. So it'll be on the Wiley Plus website. Make sure you get access to that. Some of you had various problems, and we hope mostly worked them out. If you get stuck, let me know. All right. So a few things left over from last time, or things that I blasted through and didn't do proper justice to. And one of the advantages of having some feedback, and okay, so these little messages coming to me, keep them going, and or raise your hand and speak up during class. So here are some of the things that you all questioned by way of the messages and things I left behind. First is a simple one, just a question to remind you again, what's the difference between a scalar and a vector? And the names are intimidating, but the concepts are just not much. Scalar is a physical quantity, or simply a quantity of the type that you're most familiar with. It has no direction. It's just an amount. And nearly all of the physical quantities, in fact, maybe all of them, have a number, a numerical amount, and a unit, like 1 cup, 12 inches, 5 seconds. Those are all scalar quantities. There's no direction associated with them. So, questions about a scalar? It's got 2 A's in it. That's just the fancy name for these quantities. The other kind of quantity that shows up in this class, and shows up now, is a vector. Vector has a direction to it, and I can't let that out. I can't omit it. It's part of position. It's part of velocity. It's part of force. They point in some direction. Again, it's a numerical amount, or an amount with a unit typically. 1 foot east. Now that's a vector. Now that's a position. 10 miles per hour. That's a scalar so far. Towards Richmond. Now it's a vector. Okay? And one of the questions that came up too was is velocity a vector quantity? And the answer is yes. And that's what distinguishes it from speed. So public service announcement, I do these a lot, and soapboxes as well. But a public service announcement is that speed and velocity are not actually interchangeable. It's not like velocity, to a physicist at least, or to a scientist. They're used interchangeably in common language, as though velocity is somehow a fancy word. If you want to sound pompous, you use velocity instead of speed. Not really. The issue is that velocity has added information. It's got the direction to it. So speed is the amount, how fast you're moving. We don't know where you're going. If we say your speed and which way you're traveling, now we've got your whole velocity. All right? So having said that, then let me go back to a key thing that I underdid, and that is this, that acceleration measures the rate at which velocity is changing with time. I think I said that much so far. So if your velocity is one value now and it's a different value now, a second later, you have accelerated. So that means it's a change in time. The key thing I left out is that any change in velocity is an acceleration. You don't have to change your speed. You can change the direction of your velocity. That means you're accelerating. All right? So what's an example of that? Traveling steadily in a circle, like on a carousel, and this is where I brought it up last time and didn't do justice to it. If to travel at constant velocity, I have to go at a constant speed, I'm doing it, and I have to travel in a straight line, same direction. If I travel at constant speed but travel in a circle, watch what happens. So here I'm going. My velocity is changing. This is my velocity. Okay, it's a little arrow. Vectors are often drawn as arrows. They have the length is the amount, fancy word for amount is magnitude, I don't care. So the amount, and the direction is the direction I'm pointing. And you'll notice that although the amount is not changing, I'm going at a steady speed to the extent I can. The direction is definitely changing. I'm heading away from you, to your left, toward you, and so on. Is that okay? So I'm accelerating. As we'll see down the road when I do talk about carousels and roller coasters, the acceleration, if you're going steadily in a circle, steady speed, in a true circle, the acceleration amazingly, I mean, it's not a coincidence, but it is, it's toward the center of the circle. So my velocity is this way, but I'm changing it that way. So I steer always to the left, to my left, and I travel in a circle. And this kind of motion, because it's an acceleration, doesn't happen by coasting. And let me also say 2 cents about coasting. The words that all mean the same thing or imply the same thing. If you've got net force 0 on you, that is no overall force. Hey, Newton's first law describes you travel in a straight line at a steady pace. In other words, you move at constant velocity. So if net force on you is 0, you don't accelerate, and you move at a steady, constant velocity, we can say you're coasting. That's what coasting means. So in common language, it's a little fuzzy, but to a scientist, what does it mean to coast? It means to travel as inertia suggests. You're traveling at constant velocity. And to say that you're inertial is the same thing. So to say you're coasting or inertial or have net force 0 or no acceleration, they're all the same thing. They're all the same motion. Is that okay? So no inertial object travels in a circle. Can't happen. Inertia says go straight. Traveling in a circle, that's not straight. So you have to be pushed to travel in a circle. And the push causes the acceleration toward the center, which is necessary to travel in a circle. All right? Any questions about this stuff too? That said, then let me look at the demonstrations that I did last time at the end in a hurry, because again, they're tools for a living. So like your socks come out of the dryer looking like this, bunched up. You can disentangle them by hand, or you can make use of inertia and that whole concept. That most of the sock, or parts of the sock are not going to accelerate without a force acting on them. So if you get the sock moving in one direction, and then you stop part of it, the other part will tend to coast, to keep going, doing what it was doing. It's okay? And so in principle, you can just do that. You get it going, during which time it's not inertial. I'll do it slow. So it's not inertial now. Now it's inertial, and now I'm stopping just the neck, and the rest would keep on going. Well, I can't get enough acceleration to show you, in that case, to show you the bulk of the sock continuing and pulling out, basically stretching out into a long disentangled stock. I need more acceleration, and I need a sustained acceleration. So simply wrapping it is not going to do it. But I can get a sustained acceleration by taking it around in a circle. And that's the point. If I whip this, I'll go slow first. If I whip this around in a circle, it's accelerating sort of toward my shoulder the whole time. And the force involved, because I'm going slowly, is small. I'm pulling inward on the neck of the sock gently right now, and causing the whole sock comes with me. But if I go really fast, I can make it so that I make the neck of the sock accelerate toward the center, but the rest of the sock tries to be inertial. It's not got enough forces acting on it to bend its path, and it leaves. It tries to go straight. And then, okay, so it pulled out. And it's important that you understand why that happens. I mean, it's important to me. I hope it's important to you. that it's an acceleration issue. Basically, I pulled the neck of the sock toward me so hard, it left the rest of the sock behind. It let the rest of the sock keep doing what it was doing. And that ultimately stretched the sock out. Any questions about that idea? If you don't understand it, ask me. Speak up. All right. So that's useful for, for socks. It's useful for all the sauces and shampoos and whatever, ointments and potions and whatever that you get. If you get a container like this, and the last dribs and drabs are down here in the bottom, and you can't get them out, but they're not there. They're not there at the neck. How do you get them to the neck? Well, a way is you pound like this, you break the neck and all that. That's using inertia. That is using inertia. That is, you get the stuff moving and the bottle moving, and then you stop the bottle suddenly. And the ointment, or the sunscreen in this case, continues. It has trouble accelerating with the bottle. If you stopping the bottle suddenly is an acceleration. The bottle is accelerating away from the table. And the ointment just keeps going and goes to the neck. But a more effective way, really, is this sustained acceleration of traveling in a circle. So go like that. And you can whip the whole container toward the end. The sunscreen is trying to go straight. And you're yanking the bottle out from under it. And it just keeps on going, and it smashes into the end of the bottle. All right? Ketchup, the whole thing. So I expect to have some disasters at restaurants that I want to hear about, where you whip the ketchup like that, the top comes off and the ketchup keeps going straight, and you can imagine. All right? So tools for living. Hopefully that's all right. One more thing left behind that's worth dealing with. Elevator. So when you're in an elevator that's going up, I asked you a question about that had that, and the question that came in is the elevator not accelerating because they're resisting gravity to move up the floors? Basically, what's going on here is my interpretation of that question. When you're moving up in an elevator, well, when you're moving up in an elevator and you're in the middle floors, not the start, not the stop, but in the middle, you're typically going at a constant speed upward. You've already picked up speed. You did that in the first 2 floors. You're now moving steadily upward. So speed is constant, direction of travel obviously constant. You're at constant velocity. And so all these words apply to you. Net force 0, zero acceleration, you're coasting, you're inertial. And it's true, you actually are. You're coasting upward to the top floor, toward the top floor of the skyscraper. And how can that be? Isn't gravity yanking you downward and stuff? And the answer is yes. You are being pulled downward by gravity, which is the topic for today, but you're also being pushed upward by the floor. And those two forces are in opposite directions. Gravity down, floor up, and they perfectly cancel in this case. And how do we know that? Because you're moving at constant velocity. You can't be accelerating. So they must cancel, because forces cause acceleration. And so it's true in riding an elevator. In the middle portion of the trip, you're net force 0, you're coasting. There are other interesting things going on, and the elevator's working hard to get you up, but that's another story. This is true of an escalator. When you're in the middle of an escalator and you're traveling from the ground floor to the first floor, the second floor, whatever they label them, in the middle, you're coasting. You're traveling at constant velocity. The net force on you is 0. The only two forces that are around are your weight downward, that's gravity, and the floor, the step pushing up, straight up on you. Nothing's pushing you toward the destination. You're coasting toward the destination. You've been heading that direction, so you keep doing what you're doing. And that notion that you keep doing what you're doing, that velocity, that your direction of travel and how fast you go have to do with your history, not with what's pushing on you, is counterintuitive. Let me make sure I say this to my satisfaction, hopefully it's to your satisfaction too, is that forces, the push on you, doesn't cause your velocity. You don't have to push on something for it to be moving. If you push on something, you cause not velocity, you cause acceleration. assuming nothing's fighting back, no other pushes. If you push on something, you cause it to accelerate, to change its velocity. But its velocity at the moment doesn't depend on your push. It depends on what it was doing before, because it's inertial. It's got inertia to it. It's doing what it used to be doing, maybe with some modification if you push. All right? So when you're traveling that escalator towards the second floor landing, you don't have to be pushed towards the escalator. That was done long ago. You got aimed toward it, and now you're coasting toward it. How about going down in an elevator? Same thing. And when an elevator is descending steadily in the middle ground, you are also net force zero, coasting, inertial, all that stuff. And in fact, interestingly, and it's a thought experiment, when you're in that middle territory, either heading up or heading down, and the net force on you is zero, you can't actually tell by feeling which way you're going. You can't tell if you're going up or going down. When you're coasting, you're just inertial. You can't tell whether you're moving or not. There's nothing you feel. And that's true when you're in a train heading, if you get on a metro, you get a metro and sometimes the seats are facing forward and sometimes the seats are facing backward, and you wake up in the middle having fallen asleep and you can't tell without looking. You wake up and your eyes are so closed. You can't tell whether you're heading this way or heading that way or even this way. You're just coasting. We'll talk about the feelings that you have in riding when you turn. You can feel accelerations. You can't feel velocity because it doesn't take any pushes to have velocity. It takes pushes to have acceleration. You can feel it. All right? All right, so falling balls is really the topic to get to. And let me start with a question about falling balls. So I'm going to be talking about motions like that and that and that. So hopefully you've watched, and I again encourage you to watch the lecture video, and I'm going to try to flesh it out and illustrate it. But let me start with a question here. There. And I didn't turn on the machine. Power. Turn on the main. All right. So this will show up in a minute. Plan ahead. But I'll ask you the question just live. It's easy. The question's simple. The question asked, when I throw a ball upward, and it's no longer in my hand. So it's rising, but I'm not touching it. The question is there an upward force on it? So not yet, not yet, not yet. Now, is there an upward force on it? A is yes, B is no. You can try it blind. Is this going to come on for me? There it is. Yay. All right. So there's the question. I'll give you a few more seconds here. 5, 4, 3, 2, 1. Overwhelmingly, no. Well, then why is it going upward? You tell me. Inertia. It's going upward because that's what it was doing a moment ago, and it can't stop. It can't stop. Gravity is pulling downward on it, and that is changing its velocity, but for the moment, its velocity is very similar to its velocity a second ago, and its velocity a second ago was upward. So it's coasting upward. And if there were no gravity, I can get rid of this guy, get rid of that. Let me undo this and come back to the real world. So if there were no gravity and no ceiling, and I threw it upward, once it left my hand, it would be inertial. There'd be no other forces acting on it. And we're neglecting air effects. That was part of the question. So the only thing touching it is the air, and the air is we're ignoring. It would just go head off into space, never stop. So it's, in effect, it's trying to do that, and I love to anthropomorphize stuff. So the ball is trying to go to the, up that way forever, and gravity is reeling it in. And the way gravity reels it in is to slow its ascent, bring it momentarily to a stop. There will be an instant when it's not rising or falling, and then it will begin to descend faster and faster. All right? But there's nothing pushing it up. The only force involved in the story now is downward. So I'll deal with that, and I'm glad that most of you got that correct. Those of you who didn't, stare at it a couple times. Revisit it. You don't have to push on something for it to be moving in a particular direction. It does that because it used to be doing that, and it likes to continue doing what it was doing. That's how our universe, the inertia of our universe. Okay, so I have another one. Another question to ask you here. If you hold a ball still, which the jargon term for that is at rest, and let go of it, drop it. So hold it at rest and drop it. Here's the question. What happens? And it's a wordy question. Any questions about the question? So take a look at it and ask me if something's unclear. I write these things and sometimes mess up or am too terse. All right, I'll give you another. And is that you're welcome to talk among yourselves about these questions as we do it. So the point is to understand it. If your neighbor can tell you why one's right or one's whatever, if you can work it out, hey, great. Now I'll go to 60 seconds. Five, 4, 3, 2, 1. B is the right answer. Okay, so 60% of you are getting B. But let's look at the other ones just to get an idea of what's the issue. So I'll point out with B. Velocity increases steadily in the downward direction. The ball has a velocity initially at 0, and as it descends, its velocity is no longer 0, it's downward, and it's downward more and downward more and downward more. It continues to build up speed in the downward direction. That is actually the correct answer. The other ones are the velocity becomes constant in the downward direction. It's tempting to think that at the moment you let go of the ball, it suddenly jumps to a fast speed and just continues. And that's not true. And a way to figure that out, that it's not true, is to, I don't actually want to go to the bowling ball, is to take, so like Alex here, if I drop it, you hold your hand out like this, and I drop it, flip your hand over so it's more threatening, right? You can't even catch the thing. Drop like this, not a problem. But if I drop it like this, it's a little more threatening, right? And if I had, okay, and you move your tablet out, thank you. The point being, you know that the height of the drop matters, and that as it has more distance to fall, it goes faster. All right? So you know that intuitively, and here's it's real. It does go faster and faster. Neglecting the air, it keeps going faster and indefinitely. So A is out. It's not a constant velocity. It's an endlessly increasing velocity in the downward direction. Acceleration increases steadily in the downward direction. This is tempting too, but it's not the case. It turns out that ball, well, the ball in this case, the ball experiences a constant downward force. What force? The force due to gravity, okay? It's constant. For all practical purposes, it's constant. And constant forces assuming that it's the only force, so it's the net force. A constant force on something causes a constant acceleration on it. It can't change its mass. It's got the same force. So the same force divided by the same mass gives the same acceleration. So the acceleration is not increasing. It's a steady acceleration. So it turns out falling objects have a steady downward acceleration, which is a neat result. It has it's important. It actually does interesting things. So the acceleration is not increasing steadily. That's the bottom line. Is there a term for the rate of change for acceleration? Similar to how velocity is a rate of change. Acceleration is the rate of change of velocity. Is there something that's the rate of change of acceleration? And the answer is yes. It's very rarely used. I've never used it in anything important. It's actually called jerk. Okay? You don't need to know it. But yes, people do care about the rate at which acceleration is changing. All right? What was the letter answer to the question again? Is B. B is the right answer here. Velocity increases steadily in the downward direction. All right, other ones here. Velocity and acceleration are both constant. Oh, come on. In the downward direction. Well, that's not going to work because acceleration is the rate at which velocity is changing with time. So if the acceleration is any value other than 0, the velocity is going to be changing with time by definition of what acceleration is. So you can't have velocity be constant and acceleration be anything other than 0. Is that okay? And the last one, position shifts downward steadily as time passes. That's not true either. As you drop the ball and it picks up speed in the downward direction, it travels farther and farther with every second. So its position changes slowly at first and then faster and faster and faster. It covers more distance in the later seconds than in the earlier seconds. Any questions then about this question? Because it sort of drags us across a whole lot of issues. Doesn't it eventually, drop ball, reach a constant velocity of drop from high enough? And the answer is yes, that is true, but it violates one of my assumptions that I stated. Well, I didn't put it here. And that is, if you let air, if you consider air in the story, and I'll come back here so you all can see me, or I can see me. If you include air, now there's another force around, at least more than one, but air resistance. So as the ball is dropping, it has air resistance. And you all felt air resistance when you've moved fast. On a bicycle, you stick your hand out the window of a car, and we'll do all these things down the road. But you feel that force from the air. And as the ball falls from great height, and it's going faster and faster, the air rushing up at it pushes on it. And it pushes it, you think about it, you think it's rushing downward, the air pushes it upward, fights its descent. And that upward force gets stronger as the ball goes faster. And there comes a time when the downward force due to gravity and that upward air resistance force cancel. The upward force is so strong. If you ever gone, they have these. If you've gone skydiving, you felt this force for sure. And if you have gone to one of these places where they have a fan blowing up at you and you can skydive like in a building, same idea. That upward force is strong enough that it cancels your weight. Weight being the force due to gravity, which we're doing shortly. And when that happens, your net force 0 again, which means you're not accelerating, which means you're coasting and you're inertia, the whole thing. And so stuff that falls far enough and fast enough reaches a point where it stops accelerating downward in the real world. The air just does it. For people, that's somewhere between 100 and 200 miles an hour, depending on how compact you are. Like if you're all wide out, it's like 100 miles an hour. If you're tucked in a tight tuck, you can get to 200 miles an hour when you reach that. It is called, you have a familiar name, it's called terminal velocity. It's the maximum speed. It's the speed at which you sort of settle down in falling vertically. For other things, they can go faster. Famously, you get famous for random stuff. Falling pennies off the Empire State Building, I seem to be the go-to guy. It's about 25 miles an hour is all the speed that a penny will hit when you drop it off the Empire State Building, because it flutters. It comes down like a butterfly. And the terminal velocity for a penny is only about 25 miles an hour. And you can catch it if you're able to catch. I'm a terrible catch, and so I've been filmed. I appeared on some show, failing to catch the pennies. They were bouncing off me. But don't worry about pennies coming off the Empire State Building. It's not a deal. It's not dangerous. The stuff that is dangerous is stuff that has a higher terminal velocity and that is more streamlined. And we'll talk about what streamline is in the months. And things like a ballpoint pen I would worry about. So if you just go and dump your purse off the Empire State Building, the pennies, not a hazard. It's the other stuff that's sort of pointy and slices nicely through the air that just goes to a very high speed, and watch out below. All right? Constant velocity can be reached if the air resistance equals the force of gravity. Almost exactly right. The air resistance and the force of gravity are equal in amount, but opposite in direction. That's the only quibble I'll put in there. So they sum to 0. When you add them up, two people are fighting over the skater. One's pulling you to the left, one's pulling you to the right. They pull equally hard, sum to 0. No acceleration. All right? All right. So let's go to when you drop a ball downward. So where's the whole story here? Get the physics issues done. And then when I let go of the ball, in that instant after I let go of the ball, it's experiencing only one force. Again, we're setting aside air now. Only one force, the downward pull due to gravity. So what's that like? And it turns out the downward pull due to gravity, it's due to the Earth. So it's this big planet below us that's doing it. In reality, everything exerts gravitational forces on everything else in our entire universe. You all are exerting gravitational forces on each other. And they are measurable in the laboratory. Believe it or not, there are gadgets that can study the force between one object and another object, and by way of gravity, it's really weak. The only thing large enough, with enough substance, really enough mass, near us is the Earth, for us to easily notice. It turns out that the sun and the moon exert enough gravitational attraction here on Earth that they do cause things that we do notice. Not so directly, but things like the tides. The tides are caused by the moon and the sun's gravity. And that's also in our future. So the Earth is the deal for gravity. And we're pulled towards its center. It's not a geometric center. We're pulled toward the center of its mass. And mass being this same concept we talked about days ago of how hard it is to accelerate something. That's its mass. It's the measure of its inertia. Oddly enough, the measure of its inertia also shows up in the context of gravity. That we're attracted towards the Earth because it's got so much mass. It creates a lot of gravity. All right? So we're pulled downward. Everything's pulled downward. The ball is pulled downward by gravity. And two names for that force. So the ball. Two names for the force due to gravity on the ball. We can call it the force due to gravity on the ball. That's one name for it. And more technically, the force due to the Earth's gravity on the ball. Or we can just simplify it. We'll call it the ball's weight. So that these are synonymous. The ball's weight is the force due to gravity of the Earth on the ball. And it is on the ball. So the ball is being pulled down by this force. All right? And when that's the only force on the ball falls. So that is the definition of falling. The definition of falling is an object is falling when the only force acting on it is its weight. I'm not falling right now, not because I don't have a weight, but because the floor is balancing that weight. It's pushing me up hard enough that to cancel my weight, I'm net force 0 and I'm not going anywhere. not accelerating. All right? So, because the ball experiences a weight that was, I should say, the force of gravity doesn't change noticeably. It's not exactly perfectly constant. But here near the Earth's surface, the force of gravity here on this ball, as in its weight, is the same as its weight here, as same as its weight up there. Okay? It's not, the weight's not changing. Same downward force. And if that's the only force acting on the ball, so that it's the net force on the ball accelerates in response to a steady force. So it's a steady acceleration. So that's one observation about the acceleration caused, the acceleration of a falling object. So the acceleration of an object experiencing only its weight is constant. That's kind of nice. There's none of this jerk around. You know, I won't make jokes. I can make, yeah. All right, I'll stop. Curb my enthusiasm here. So, when I let go of the ball, it undergoes a constant downward acceleration. Downward because it's toward the center of the Earth's center of mass. It's straight down. It defines downward. You know, what is downward? It's all about gravity in the Earth. Otherwise, you know, way out in space, there's no upward and downward. Doesn't mean anything. So I wanted to ask this question. Any questions before I go here? Venmo. Yes. All right. All kinds of random things can show up. This question. So I've been playing with a baseball. What if I go over to a golf ball and I say, you know, a baseball weighs approximately 3 times as much as a golf ball. It's easy to figure this out or to notice this. If I drop them side by side from rest, again, the jargon being that I hold them stationary and let go, same time, which hits the ground first? You okay with the question? Let me turn on the... So I'll give you the 30-second point. Four, three, two, one, clickety. Oh, come on. There it is. And C it is. So 80% of you came up with C. And I would say it didn't have to be this way. It turns out this is the answer, but I want to show you why. Because it's actually a, well, somewhat remarkable result. You know, I should have done it like this. What's the answer? Ah, ready? Get set. They fall together. That is actually, all right, all right. When I first was drafting the question, I was thinking of the bowling ball. And I have dropped the bowling ball on the floor by accident over the years a couple of times, and it concerns the people in the downstairs. They come up. All right, that's actually a remarkable result, that the two fall together. Stuff falls at the same rate, no matter what it is. Random example, you drop all the change out of your wallet. You're literally going for broke off the Empire State Building. You drop all the change at once. Quarters, nickels, dimes, whip. Yeah, I didn't drop it I dribbled it out of my hand. But it all goes together, apart from the air resistance problems. That's actually a remarkable thing. And how does it happen? So, you know, you might go like, well, of course it's, no, you know, no duh, of course it happens. Why? So here's the story. The baseball weighs 3 times as much as the golf ball. I told you that from the get-go. That means if that were the only difference between them, it would be pulled downward 3 times as hard. Well, that sure makes it sound like it should accelerate 3 times as fast. It should pick up speed and cover the distance much faster and hit the ground first. So you can follow that idea so far? But there's a second issue around. It turns out that weight and mass go together. An object that is 3 times as heavy as the baseball is 3 times as heavy as the golf ball. That's weight. That's what gravity has opinion. Weirdly enough, the baseball has 3 times the mass of the golf ball, meaning it's 3 times as hard to accelerate as the golf ball. So the baseball is pulled, if that were the only difference between these two, if it was only that the baseball was 3 times the mass of the golf ball, the baseball would be hard to accelerate, it would lag behind, and the golf ball would hit first. So to summarize, if the baseball were just heavier, it would go faster. It would accelerate faster. If the baseball were just more massive, it would go slower. But it's both, and they cancel perfectly. So even though the baseball is pulled down 3 times as hard, it resists the acceleration 3 times as much. And it accelerates the same as the golf ball. Does it need to be proportional, like the 3 times the weight and 3 times the mass? Yes, those two go together. It turns out that an object's weight here near the surface of the Earth is exactly proportional to its mass. You double it, if you pick an object that has 3 times the mass, it also has 3 times the weight every single time. And it didn't have to be that way, or maybe it did in the grand scheme of the cosmos. Maybe it had to be that way, but it is that way. Why is mass showing up in a gravity story? Or why is gravity showing up in a mass story? They're separate quantities. Weight is how hard gravity pulls down on the ball. Mass is how hard it is to make the ball accelerate. And it has nothing to do with gravity. You can have mass out in deep space where there's no gravity for all practical purposes. You can be out there in center of the, between galaxies, and you go like this, it's still got the same mass it did here on Earth. But bring it here to the Earth, if it's got 1 unit of mass, it gets 1 unit of weight. Got 2 units of mass, it's got 2 units of weight. Wow, that's weird. I hope you can appreciate that they don't necessarily have to go together in some fantasy universe, but they do. And the consequence is that everything accelerates at the same rate. How's that? If you pick an object that's got 3 times the mass, it's also got 3 times the weight, and those two work together to make it fall at the same rate as the first object. How would a basketball and hollow ball factor into this? As long as we're neglecting air resistance, hollow doesn't matter. So none of these are going to experience significant air resistance in this particular situation. They all go together. Is that okay? Where it does matter is this race between these two objects. And whatever the weight difference is, the mass difference is corresponding. They go together. And when I let go of them, they fall together. Oops. The problem is air resistance. This guy gets negligible air resistance. This guy, not so much. Can you think of a way in which I can protect this from air resistance, the sheet of paper? I heard a book. Did I hear what? Feed. Folding it. If I wadded it up into a really tight nugget, it would fall properly. But I have another trick for doing this. I'm going to let it follow another object that's falling. Okay? They're not glued together. The paper is going to do it. It's going to have to fall. There's no reason why it would go down otherwise. But the book is going to get the air out of the way. Can I do this? Okay? They all go together. All right? So what determines that acceleration. That acceleration, it has a name. It's called the acceleration due to gravity. It's universal here near the surface of the Earth. It has an approximate value that is, okay, in the world of metric units, familiar to you or not. The metric unit of distance is this, the meter. Metric unit of time, fortunately, is the second. And the metric unit of acceleration, because acceleration is the rate at which velocity is changing, and velocity has the units meters per second, like miles per hour, meters per second. The unit of acceleration is the meter per second, or the meter per second squared. Whether you get the units or not, I don't care. It's not crucial. But the unit of the acceleration due to gravity here near the surface of the Earth is about 9.8 meters per second squared, which means that a dropped object acquires a downward velocity. Its velocity, well, I should say, changes in the downward direction by 9.8 meters per second every second. And that constant actually comes, I'll let it go. That constant is actually the ratio of pick any object, the golf ball that got away from me. If you take, or this baseball, if you take this baseball's weight and divide it by the baseball's mass, it comes out to 9.8. And the units, oddly enough, can be finagled into meters per second squared. The ratio of the weight to the mass. That's Newton's second. It comes up because of Newton's second law, which has a force over a mass gives you an acceleration. And similarly, the weight of an object over its mass gives you an acceleration. In this case, the acceleration due to gravity. Let me see where I want to try to leave us. Okay, so if I drop this ball, its weight is the only force acting on it. It accelerates downward at this famous acceleration due to gravity. And that means its velocity increases in the downward direction steadily by 9.8 meters per second every second. What that does is it means the ball travels short distances in the first 1 second, 2 seconds, 3 seconds. It's not traveling very far, although it's traveling farther in the later seconds than in the earlier seconds. But toward the end of its fall, it's traveling very fast, covering a lot of distance per second. So you can have situations, and I'll save that part. When you watch something fall, it doesn't travel very far in the first half of its fall as measured by time. So if it falls, I'll go back to this. But if it falls for 5 seconds, I pick a number that I can divide by half. 4 seconds. In the first half of that fall in time, that is the first 2 seconds, it doesn't travel very far because it's not moving very fast. It travels most of its distance in the second pair of seconds because it's already accumulated a lot of downward speed. And where does this show up? It's a public service announcement. If you're trying to do a bungee jump or a drop tower, so you've got an amusement park and you're trying to do fun games for your friends and relatives. If you drop them just for 1 second in time, they don't travel very far. You can make a short drop tower. I'm sure many of you have gone to drop towers like King's Dominion has one. And it's 1 second to drop, you don't travel very far. 2 seconds to drop, you travel a lot farther. Because that second, you started it moving downward and you finish it moving downward a lot, really fast. So 2 seconds, you can sort of do this. A 5 second drop tower is crazy, it's too high. You travel so far in that fifth second, it's uneconomical. So this is why drop towers are about a 2 second drop. That's about all they can afford to build. That last few seconds, too much. Same with bungee jumps. You can't make a bungee jump that's a 10-second fall. You travel so far in the last seconds, you'd have to have the Grand Canyon wide open, and you might be able to pull it off. All right? So with that, I'll stop, and I'll continue falling balls on Friday.